So page 770, section 11.1. They start off here reminding us about the three-dimensional coordinate system. All right, we have talked about the three-dimensional coordinate system before. Remember, that was the one that we said that X is going to go forward and backward, Y is going to go left and right, Z is going to go up and down. So that's different for us. We also said that it kind of looks like a corner. So if you are trying to envision this, you're sitting in your bedroom working on homework, you can look at the corner of your bedroom or the corner of the classroom during the test or a quiz to just kind of help you see in 3 dimensions. They also show us that if you are looking at the plane that intersects the X axis and the Y axis, then that would just be this XY plane down here. Remember that we mentioned when you graph in 3 dimensions, instead of getting a line, you get a line with that 3rd dimension, that thickness to it, so you get a plane that extends infinitely in all directions. And so they illustrate those 3 different planes for you here. And again, an illustration we've seen before, this point would be the solution that we were getting when we were solving systems of 3 equations with 3 unknowns, where we were solving for x, y, and z. So we would get something like x equals 1, y equals 2, z equals 3, and that would be that one point where all of our planes were intersecting right there in the center. Now, how do I plot a point in 3 dimensions? We've looked at graphing planes in 3 dimensions, but we've not plotted points in 3 dimensions. So they tell me on page 770 that we're going to work with a 3-dimensional coordinate system. They talk about the 3 different planes that we looked at in our diagram. They tell me that those planes separate the 3-dimensional coordinate system into 8 octants. Normally we would have quadrants when we have 4 pieces. There are 8 pieces here, so they're octants. And they say that a 3-dimensional coordinate system can have either a left-handed or a right-handed orientation. In this text, we're going to work exclusively with right-handed systems, and you see that, thumb there in the textbook where they're illustrating that for you. So if I want to plot a point in 3 dimensions, I'm going to start with the x and the y value. So for our first point, we want to plot 2, -3, 3. My x value is 2, my y value is -3. So I'm going to say, okay, here's a +2 on x, here's a -3 on y. I'm going to use those 2 sides as 2 sides of a parallelogram and let them be my guide for drawing the other 2 sides of the parallelogram. So I had the +2 here, I'll draw a parallel side to that. I had the -3 here, I'll draw a parallel side to that. From the point of the parallelogram where I drew the 2 sides and those 2 points touch, feels a little bit like the vectors that we were working with, right? Parallelogram method, and our resultant would go from the starting point across the diagonal to the end point of that parallelogram. So it's like that same point that we were drawing our resultant to. If I go to this point, the tip of my parallelogram, from that point I will either go up or down my z value. And for this particular problem, our z value was a +3. So I'm going to start right here, and I'm going to go up 3, so up 1, 2, 3, and that puts me at this point right here. That is 2, -3, 3. Now, something to point out to you is in order for us to clearly see all 3 dimensions, I kind of have to have a perspective where I'm not looking straight dead on at this. I'm kind of looking down at it, or I'm looking up at it. And so the way that we've drawn this is like we're looking down on this 3-dimensional system. And so for that reason, notice that our z value did not come all the way up to a +3. It looks like it's down here at maybe about 1.5. The reason for that, again, is just our perspective. If the way that we were looking at it, if you'll notice, this z value looks to be starting down here at like -1.5. So that's why when we go up 3, we're only up here at +1.5. We're not all the way up at 3. All right, let's look at another one of those. Let's graph -2, 4, -3. So I'm going to start with x is a -2. So I'll come back 2 on the x-axis and put my point there. Y is a +4, so I'll come to the right 4 on the y-axis. And those are going to be 2 sides of my parallelogram, so I'm going to draw parallel sides to those to give me the rest of my parallelogram. And I'm going to go from the tip of that parallelogram where the two lines that I drew touched. I'm going to go from that tip up or down my z-value. And this time my z-value is a -3, so from right here I'm going to go down 3, and when I do that, there will be my final point. And again, because of that perspective, I'm not actually coming all the way down here to -3 and coming over and plotting that point. It's a little higher up than that, because when we started drawing it, it was almost like we were up here at almost at a +2 when we start coming down 3. All right, the next thing that they show me in the middle of page 771 is that there are several formulas that we already know how to use in 2 dimensions that we can expand and then use the same formula in 3 dimensions. So if I have a 2-dimensional point that is x1, y1, and a 2-dimensional point x2, y2, so 2 points, we typically label them in that way. If I wanted to find the distance, I'd find the difference between the x's squared, add it to the difference between the y squared, and then take the square root of that. That's our typical distance formula. If I have 3 dimensions, then I want to do the exact same thing. I just want to expand that formula to the 3rd dimension. So I'm still going to do the difference of the x's squared, the difference of the y squared, but I'm going to take that one step further and also do the difference between the z's squared. Let's say I wanted to find midpoint. The midpoint formula that we learned back in August of this year was add your 2 x's, divide by 2, add your 2 y's, divide by 2. So expand that to a 3rd dimension, and that would be add your 2 z's and divide by 2. If I take the equation of a circle, we were just working with this not too long ago with conic sections, and we worked with it earlier at the beginning of the year. But if I take the equation of a circle and I add a 3rd dimension to a circle, it becomes a sphere, like a ball. So that equation will start the same way. X minus h squared plus y minus k squared is equal to r squared. But here's our 3rd component. For that 3rd dimension, I'm going to add in z minus j squared. So HKJ will be the center of that sphere, and R will be the radius. So let's look at how we can use those formulas that we're familiar with, expanded to 3 dimensions, to help us solve some problems. So examples 2 and 3, they're going to give me 2 points and ask me to find distance and midpoint. So let's say that they gave me 5, -2, 3, and they gave me 0, 4, 4. I'm going to go through and label these the exact same way that we did when we were working with just 2 dimensions, x and y. And I'm going to come down to my formula, and in my formula, I'm going to do x2 minus x1, that quantity squared. So I can come up here and say x2, 0, minus x1, 5, and I'm going to have 0 minus 5, that quantity squared. What would I get for my y values? What minus what down here? Yeah, 4 minus a -2, so 4 plus 2. How about my z values? 4 minus 3. So let's go ahead and simplify. -5 squared is 25, 6 squared is 36, and 1 squared is 1. And we can combine those values to get square root of 62. Now, if that radical could be simplified, I would reduce it down. But 62 is just 31 times 2. Both of those are prime. I can't simplify that radical any further. I could give a decimal approximation for it if they wanted that, but typically they want the exact value. All right, what about midpoint? When I'm doing midpoint, I typically go through and take the first x value 5 and the second x value 0 and add them and divide by 2. So what would I have for the numerator of my y values? I'm going to have the -2 and the 4 for the numerator for my y values. What am I going to have for the numerator of my z values? 3 and 4, yeah. So what am I going to get from my midpoint in 3 dimensions? Yes, 5 halves, 1, 7 halves. All right, equation of a sphere. This was the equation that we had higher up on the page for the equation of a sphere, and we said that would be a center of HKJ and a radius of R. So we can go through and say, okay, if h is 3, then we're going to come down here and say x minus h. That would just be x minus 3 squared. Then y minus what? -1, right. So y minus a -1 or y plus 1. How about z? Yeah, z minus a -2 or z plus 2. If my diameter is equal to 8, what's my radius going to be? 4, right, because if I take the diameter and divide it by 2, then that'll give me my radius. So if my radius is 4, then I'm going to come down here and slot that into my formula. It's going to be 4 squared or 16. Now, on the quiz, it's going to say 16. It's not going to say 4 squared. The reason I'm leaving it this way is just to stress to you, we square that 4 and get 16. We do not square that 4 and get 2. But that's one of the most common mistakes that I see on the equation, both in the distance formula and in the sphere formula, is that we forget whether we're supposed to square that or take the square root or what we're supposed to do. So you can be sure on your quiz that one of the choices will be that it's equal to 16 and one of the choices will be that it's equal to 2, because I need to see, do you know whether to square that or square root that? Okay, so for this one, they gave me the information and they asked me to come up with the equation. So for the next one, they're going to give me the equation and ask me to come up with the information. And of course, they can't give me the equation in standard form. That would be too simple. So what do we have to do to get it in standard form? Complete the square. And we get to do it 3 times. Yay! Alright, so let's get all of our x's together and leave room to complete the square. Get all of our y's together, leave room to complete the square. Get all of our z's together, leave room to complete the square. And move our constant over to the other side so that it is out of our way. Alright, so remember, when we complete the square, we take the coefficient of the middle term, -2, cut that in half, -1, and square that, +1, and we add that to both sides. Alright, so what is the coefficient of the middle term for y? 4. Cut it in half. 2. Square it. 4. Right, and we're going to add that to both sides. For z, what's the coefficient of the middle term? -6. Cut it in half. -3. Square it. +9. Good. Add that to both sides. So if we've done this correctly, we have created a perfect square here, a perfect square here, and a perfect square here. So let's write them in their factored form. This is x minus 1 squared, this is y plus 2 squared, and this is z minus 3 squared. And then we can combine our constants on the right-hand side. Alright, so now I have it in standard form. Now I just need to know what my center and my radius are. So what is my center?
1, -2, and 3.
Yes, 1, -2, 3. And what's my radius?
Square root of 6.
Square root of 6. And that's another one of those that on the quiz, square root of 6 will be an option and 36 will be an option. So be careful with those. Alright, so here is our homework for tonight. Just to note that there is an answer in the back of the book that's wrong for one of the problems. So be sure that you note that so you're not working that problem repeatedly trying to make it work when it won't work.